A context-free grammar is the mathematical blueprint used to define the valid structure of a programming language. In computer science, the authoritative text on translating these languages is colloquially known as the Dragon Book. It lays out the rigorous theory behind language processors and how they read our code. For developers, context-free grammars are highly appealing because they organize syntax into clean, intuitive rules. An if statement contains an expression and a body contains statements, and the hierarchy cascades naturally downward. This split screen shows how a standard snippet of Java code perfectly maps to an abstract syntax tree. But there is a trap here. A grammar that is highly intuitive for a human to read is often mathematically unparsable by standard automated systems. Predictive top-down parsers, the algorithms that read our code, require absolute mathematical determinism. You cannot just write syntax that looks organized. You have to engineer it to survive the compiler. A top-down predictive parser operates under a strict constraint. It scans code from left to right, and it must build the syntax tree using only a finite lookahead buffer, often just a single token of text. Imagine this process as a real-time traversal. The algorithm moves down through the grammar's rules, matching the incoming text to the required structure as it goes. When the parser encounters a rule with multiple valid paths and cannot determine which one to take based on its limited lookahead, it halts. The algorithm just cannot guess. This failure is triggered by three specific grammatical flaws: ambiguity, left recursion, and structural indecision. We cannot give the parsing algorithm more intuition. Instead, we have to mathematically mutate the syntax itself, so the parser never has to make an ambiguous choice. In language theory, ambiguity occurs when a single string of code can legally produce two or more distinct parse trees. The classic example of this is the dangling else logic problem. Consider a nested sequence with an if condition, followed by a second nested if condition, but only a single else statement at the end of the block. In the first tree, the else connects upward to the outermost conditional. If the first fails, it triggers the else. In the second tree, the else connects locally to the nested conditional. If the first passes but the second fails, it triggers the else. Both structures are legal under a standard grammar. Because of this duality, the compiler is paralyzed. It cannot generate executable machine code without knowing exactly which control flow the programmer intended. To restore determinism, compilers enforce an industry-standard disambiguating rule: match each else with the closest unmatched then. Forcing this rule is the only way to guarantee a single, predictable structure. A top-down parser also follows a rigid expansion logic. It aggressively expands the leftmost non-terminal symbol in a rule before it processes any actual input. This breaks down when a grammar contains left recursion, a state where a production rule defines a variable primarily in terms of itself, placing that same variable at the very start of the rule. When the parser attempts to read a left recursive rule, like A produces A plus something, it instantly expands the first A into another A, which expands into another A. Because it hasn't read any input text yet, this creates an infinite recursive loop that consumes memory without ever advancing the input buffer. Left recursion acts as a lethal trap for predictive algorithms. To make the grammar functional, these loops must be systematically identified and eradicated. We fix this using a specific algebraic substitution that rewrites the grammar rules without altering the strings the language can generate. The goal is to replace the immediate, infinite leftward expansion with a deferred rightward expansion. We achieve this by introducing a new variable called a remainder non-terminal to facilitate the shift. Here is that infinitely deep leftward loop we saw earlier. By injecting the remainder non-terminal, we flip the execution path. The recursive calls are moved to the end of the rule, creating a structure that grows safely down to the right. Now, the parser is forced to successfully consume an actual input token before it loops. It processes the code iteratively and will eventually terminate. This mathematical substitution bridges the gap between a human's recursive mental model and the strict iterative processing limits of a machine. Predictive parsers face another dilemma. Because their lookahead buffer is usually restricted to just one token, they must make permanent structural choices while partially blind. This limitation causes a failure when a grammar contains shared prefixes. This happens when alternative rules start with the exact same sequence of symbols, but end differently. In this visual, you can see how the shared prefix acts as a smokescreen. The parser reads the first token, but it cannot see far enough ahead to know which of the two distinct endpoints it is actually heading toward. To solve this, we use a structural tactic called left factoring, which allows for deferred decision-making. We slice off the identical prefix and collapse those diverging paths into a single initial node. The tree now splits only after the shared sequence ends. This allows the parser to safely execute the common code. When forced to choose a path, it has consumed enough input to cleanly diverge. Left factoring acts as a spatial reorganization of the syntax, aligning the code structure perfectly with the chronological limits of the parser's memory. Through disambiguation, unrecursing loops, and left factoring, the naive grammar has been converted into a machine-ready state. The computational payoff of this work is that parse times are now mathematically guaranteed to operate at a highly efficient, linear scale. Yet, despite this efficiency, there are essential programming tasks that a context-free grammar is mathematically incapable of performing. Consider the identifier declaration problem. In abstract terms, this is represented by the string formula WCW. This formula tests whether a variable used deep inside a program perfectly matches a variable declared at the very beginning. As shown on this tree, the grammar's vertical hierarchy prevents horizontal data sharing. The parser cannot look across the branches to verify that the variable on the right matches the declaration on the left. A parallel failure occurs with function arguments. A context-free grammar cannot mathematically synchronize the parameter counts across separate branches of the tree. Context-free grammars possess zero memory of previously parsed branches. This establishes the strict boundary of what syntax analysis can achieve on its own. To solve these cross-branch memory failures, the compiler must transcend pure syntax. It hands the output to the next phase, semantic analysis. Here, external memory structures like symbol tables are built specifically to track context-sensitive state over the entire syntax tree. Compiler architecture is not arbitrary. Its phases map perfectly to the absolute mathematical boundaries of computational models.